Let's keep continuous the incoming inspection topic. As we know that when incoming materials are put into production and a certain proportion of defects are found, the incoming material inspection supervisor will often say, because it is a random inspection, defects may not be detected. Is this really the case? Let's try to study it more today. Welcome to the DCLT channel. Before we get into the next topic, let's review what we explained in the previous episode. In the previous one, we explained incoming material inspection in the manufacturing process, introduced the sampling inspection method and gave examples. The sampling inspection result of the case was acceptable, but in fact, after the materials were put into production, it was found that the defective rate of this batch reached 1.5%. According to the acceptance criteria, it should have been rejected if it exceeded 1.0%, but it was accepted. Let's review, that is. Since no defective products were found in this incoming material inspection, the incoming material inspection result was judged to be acceptable. However, after actually going into production, operators discovered that the defect rate was higher than 1%. This case shows that the defective rate requirement for a batch is 1.0, which means a defective rate of 1%. The defective rate requirements for samples during sampling are 2 for acceptance and 3 for rejection, that is, the defective rates are 2.5% and 3.75% respectively. The actual defective rate of the batch is 1.5%. In this case, why are the requirements different? There are some different explanations on the internet or in textbooks. Let's start with the acceptance criteria. That is, the acceptance level AC in MIL STD 105E is 2, in other words, 2 divided by the number of samples 80 is 2.5%, and the rejection level RE is 3, which is 3.75%. How is this set? And why is there a gap with the batch defect rate requirement of 1%? This is because the ratios of 2.5% and 3.75% are only sample level percentages, not lot level defective percentages. That is, the producer risk, alpha, and consumer risk, beta, have been considered from batch to sample. Explain these two risk rates below in the video. Namely, setting AC is based on the producer's risk, alpha, which is the probability of incorrectly rejecting a batch when it is actually good. The determination of RE is based on the consumer risk, beta, the probability of mistakenly accepting a batch when the batch fails. To further explain producer risk, alpha, and consumer risk, beta, it is very important to determine the risk when implementing a sampling plan. These risks represent the chance of misjudgment that may occur during sampling inspection. In this sampling plan, it is 5%, i.e. alpha equals 0.05, beta equals 0.05. Setting these risk levels can help balance the reliability of inspection with the potential for actual production losses. Therefore, AC and RE, the number of acceptable and rejected defects, are determined based on statistical theory, specifically the binomial distribution or the normal approximation. Concerning the probability distribution function, we use binomial distribution or Poisson distribution. For the number of defective items in the inspection plan, both the binomial distribution and the Poisson distribution can be applied, but the appropriate distribution is usually selected based on the AUL. Firstly, the binomial distribution. Assuming that each product is sampled independently and the probability of a defective product is P, the binomial distribution is applicable if the inspection of each product is an independent event. The formula for calculating this chance is, where n is the sample size, 80 units, k is the number of defective units found, and p is the probability of each unit being defective. The AQL here is 1.0%, which means the defect probability of each product is P equals 0.01. AC is determined based on the producer risk, alpha. Suppose we want to set the producer risk to 5%, i.e., there is a 5% chance of falsely rejecting a batch of good products. We need to find a number of defectives K equals 2. In your case, that the total probability of having 2 or fewer defective items in the sample is less than or equal to 5%. This is calculated using the cumulative probability P, x is less than or equal to 2, which calculates the values according to the binomial or Poisson distribution until the cumulative probability reaches 5%. The same for the Poisson distribution. When the number of defective items is relatively small, compared to the overall sample size, and the AQL is small, the Poisson distribution approximates the binomial distribution, especially in the case of large samples. The formula for the Poisson distribution is shown in the video, where lambda equals n times p is the expected number of defects. Since the AQL of each sample is 1.0%, the corresponding expected number of defects is lambda equals 80 times 0.01 equals 0.8. In this way, the probability of the Poisson distribution can be used to estimate the probability of finding 0, 1, 2 or 3 defective products. The same, AC can be obtained. But why can't I get defective products? For the number of defective items in the inspection plan, both the binomial distribution and the Poisson distribution can be applied, but the appropriate distribution is usually selected based on the AQL. Binomial distribution assumed is sampled independently and the probability of a defective product is P. The binomial distribution is applicable if the inspection of each product is an independent event. The formula for calculating this chance is, where n is the sample size, 80 units, k is the number of defective units found, and p is the probability of each lot being defective. The AQL is 1.0%, but the actual product defect rate is p equals 0.015. Poisson distribution. When the number of defective items is relatively small, compared to the overall sample size, and the AQL is small, the Poisson distribution approximates the binomial distribution, especially in the case of large samples. The formula for the Poisson distribution in the video, where lambda equals n times p is the expected number of defects. Since the AQL of each sample is 1.0%, the corresponding expected number of defects is lambda equals 80 times 0.015 equals 1.2. In this way, the probability of the Poisson distribution can be used to estimate the probability of finding 0, 1, 2 or 3 defective products. Next, let's take a look at the probability of getting 0, 1, 2, and 3 defective products respectively. If 0 defective, it's about 29.85%, 1 defective product is about 36.36%, 2 defective items will be about 1.69%, and 3 defective items is about 8.77%. From these probabilities, when we explain that, because it is a random inspection, defects may not be detected, it had better to also explain the probabilities of finding defective products. We have learned the process of calculating AC and RE for binomial distribution and Poisson distribution, and know that AC and RE are calculated based on the tolerable probability of defective products in the inspection batch and the expected risk level. Simply sum it up, these numbers reflect the allowable error rate in the inspection process. In actual inspection, we want a high chance that batches that meet the requirements are accepted, and a low chance that batches that do not meet the requirements are mistakenly accepted. This is usually measured in terms of false positive rate, type 1 error, and false negative rate, type 2 error. It also has the risk of consumers who should return goods but do not, or who should return goods but are accepted. It can also be said that there is a risk rate for producers who should accept goods, but do not, or who should accept goods but are returned. Alternatively, we can use normal approximation to calculate, look up standard scores or Z-score tables, etc., to find the corresponding number of defects. When the sample size is large enough, the normal distribution can be used to approximate the binomial distribution. This allows the calculation of AC and reusing the following formula. Expected value mu equals n times p, the average number of defects or the expected number of defects. Standard deviation sigma equals n times p times 1 minus p, caret 0.5. The standard score Z value is obtained according to the normal distribution, and AC and RE are the values corresponding to the given acceptance probability and rejection probability respectively. That is, when the number of defective items in a batch are between AC and RE, the batch will be accepted, otherwise it will be rejected. Here is a case study for reference. Let's look at this example calculated using a normal distribution. Firstly, we look up the Z-score table and find that 95% acceptance probability, corresponding to a Z-score of 1.645, and 5% rejection 1 is minus 1.645. AC equals mu plus ep times sigma equals 2.26 and RE equals minus 0.663. Therefore, AC is taken as 2, must be an integer, knowing that 2 defects are acceptable. And, the same, RE can be known. From this introduction, we can see that the acceptance criteria are based on the acceptance and rejection quantities obtained by following the reasonably set risk or risk rate. As an appendix, the normalization of the normal distribution, also known as the Z transformation, or the Z-score mentioned earlier, is for the convenience of knowing the probabilities simply by looking up the table, as shown in the figure. The area below the curve and the horizontal axis is 1, which means 100% probability, while the area to the left of Z equals minus 1.645 is 0.05, and the area to the left of Z equals plus 1.645 is 0.95. If we don't have a table and we want to know the probability, we need to use integration to find the area. The curve equation f of x, which is the probability density function, is somewhat complicated to calculate, so it is often obtained by looking up a table. Again, thanks for your attention.